Hello, everybody. This is applications of the second derivative, continuing chapter 4. This is section 4.2. We already saw some of it as introduction to concavity, whether it's up or down and how the rate is changing when that happened. So now we'll talk a little more about it and understand a little more of this second derivative behavior and what it implies. First, to find it, you need to find a second derivative and find its critical values by setting it to 0 or find it where it's not defined. So two things, either where the second derivative is 0 or where it is not defined. That should give you critical values if there are some. And from there, you're going to test the left and right side of each critical value to find out what happens to the second derivative there. And here is an example. Maybe you pause the video and you find these first and second, and you compare them with these. Now that we have the second derivative as 6x minus 1, it's going to be factored to get this. So we will set x minus 1 to 0, and we'll get x equal 1. And now that's the critical value, 1. And we'll test with, let's say, two numbers, left and right side of each one, and which I marked here. The negative side, when we try, let's say 0, we find out it's negative, and the right side we try it 2. So any value, of course, you can try any number as long as it's there. Any number as long as it's there, right? And we find on the right side it's positive. So it looks like this function concaves down from this side all the way to 1, and it concaves up from 1 to infinity. And if we look at the graph, we will see that. If you try to graph it, you will see that. So that's the beginning of it. For inflection point, it has to be continuous at that point first to say it's an inflection point. And the second thing, the concavity changes either from positive to negative or negative to positive. Then it's an inflection point. And we saw this in applications where the rate itself increases, then it starts to slow down. And that's an inflection point. And if you see here at each of inflection point, the graph of a function crosses its tangent line. So this is some types of inflection points, and you see when you what happens when you draw the tangent at that point, and how it crosses the graph. So we will do a method of finding the inflection point. So of course you need to find the derivative, as usual, the second one. You need to find where it is 0 or where it does not exist. And you need to test the signs. It just now, what you want to make sure is this part here, and we move across, the function moves across that point C, not to jump. Not that we have negative and positive in different places. It has to be changing sign from positive to negative or negative to positive, the second derivative, but it also passes through x. In that case, we'll say it is an inflection point. Let's see here an example for x cubed. And we are familiar with x cubed. It comes something like this and it turns. So that looks like an inflection point, right? And if you do a tangent, it's going to be something like this, right? So if you do the second derivative, 6x, you set it to 0, x equals 0 is a critical value, and you test left side and the right side by using a number. Let's say I use -1 here and I use 2 here. Then you get negative and positive. So if this is negative, means it concaves down, and here it's positive, means it concaves up. And that's what the graph shows, right? So up and down. it passes through it, so that's an inflection point. Let's talk about the second derivative test. Second derivative test, if we have, let's say, these two cases, to find out if we have a local max or a min, the first derivative does a good job in finding this. But if you want to use the second, it has to go this way. First of all, you find the first derivative and find its critical, the critical value in it, set it to 0. If the first derivative equals to 0 at this point, right? And when you plug in the x or c here, you find it's negative, means it concaves down. The first derivative tells us it's a flat horizontal line. The second derivative tells us it's concave down or opens down. If it opens down, then you have a local max. Similar thing here will happen. The first derivative equal to 0 means you have a flat line, horizontal tangent. You do the second derivative, it comes up positive. Means it, I won't say open up, but it's opening upward. And if something is upward here for this function, and it has a horizontal tangent, that means that's a local minimum happening there. And so this is kind of the procedure that I spoke about to follow. You compute the first and second. You find the critical value for where f prime equals 0, where you have a horizontal line, and you test the second derivative. Of course, C here is important to know because the second derivative, if it's 0 or it does not exist, the test fails. It does not tell us much. That is inconclusive, right? So keep in mind that this is versus the first derivative 0. This is conclusive. This tells us that you have a horizontal tangent there. So this means something. This doesn't mean much. Okay, similar thing, maybe pause the video, do first derivative, second one, ask yourself, how do you find the first derivative and how do you factor it, of course, to get the critical values x equal -2 and 4. And when you get these two values, now you want to try what is the second derivative at this number, and because we know the first derivative here, of course, is 0. At -2 is 0, at 4 is 0. So that's the first thing happen, which is this part, right? So now, and we did 1, so now in 3. So you're going to do this other part. So what are these? If you check a little more the notes, for the -2 is gives us -18. So it gives us negative, means it concave down, which means you have a local max. And I use here local or relative, so you get used to both. We use them interchangeably because they have same meaning, which means not absolute. Both these mean they are not absolute. They're only local at some interval, not all everywhere on the domain. It's just on some interval. All right. So if you do the for 4, you find it's 18. 18, which is positive, which means upward. And if it's upward, then it's a local minimum or relative minimum. All right. Comparing the first and second derivative, this is just, there are some cases where these tests don't work out if you see this, but I think the important part to know here is here that the first, as I mentioned, the first derivative f prime tell us where f is increasing and where it is decreasing. That's an important part, not to mix the two. Whereas the second derivative tell us where the graph concave up and down. And of course, we may run into cases where the second derivative does not tell much and we have to investigate the graph. And here is a summary. So this important summary to keep in mind, and you've seen this before, right? So just another reinforcement, and now you have more techniques for the tests themselves. So for the lecture activity question 1, we have this graph where it is concaving up. It looks like over negative infinity to negative 4. All open intervals, and 4 to infinity, where it concaves down between negative 4 and 4, and find the inflection point. We don't have any, does not exist, because for inflection you need it to switch. You see here, here it switches, but it is not continuous at negative 4. Same thing here, not continuous at 4. For these points to be inflection points, the graph has to pass through them. Similarly here, so concave up, we have 0 to infinity, concave down, negative infinity to 0. Do we have inflection point? Yes, because it's switching at this 0 point. It's switching from concaving, if we do left to right, it's switching from concaving down to up, or it's switching from being negative to positive, and it passes through it. So this point is 0, 1. For this example of g of x, it's negative x squared plus 6x plus 3. It's a parabola. Let's find the first and second derivative. So I would recommend you kind of try it and see if you, of course, to get something like this. Then you do the second derivative and you should get negative 2. So pause the video and try it. Then where does the function concave up or down? If you check look at the second derivative, is always negative. It's just that negative value, so there is no way for us to test, put some x values to see does this changes or not. So means it's always concave. So means we have concave down or downward, right? But concave upward does not exist, okay? And downwards, because this is a polynomial or a parabola, its domain is negative infinity to infinity. So it concave downward over negative infinity to infinity, which we already by looking at the parabola and looking at a equal negative 1, which in the past you say it opens down. Let's look at this example. It asks where concave up or down. So first we need to find the first derivative. So you can maybe sometimes pause the video and try what you learned so far in finding the first and second. So we should get 12x cubed minus like 90x squared plus 1. Then we try on its second derivative and get 36x squared minus 180 x. and we factor this 36 in x and get x minus 5. So when you set this to 0, we'll find that x equals 0 or x equals 5. So that's the important part, is factoring and not forgetting about x can be 0 when you use the zero product property, right? X can be 0 or x equals 5. So now when you put 0, 5, and you test this, the second derivative, you're going to use some values. Let's say -1, let's say 1, let's say 6. And if you use -1, you get 36 times -1 minus 5. Then it's -36 times -6, so that's a positive. If you use 1, it's 36 times 1 minus 5. It's 36 times -4. That's negative. And if you use a 6, that's 36 times 6 times 1 minus, no, that's a 6 minus 5, so 1. And 36 times 6, 216. That's positive. So for this second derivative, it looks like it's positive here, which means it concave upward, negative infinity to 0 and 5 to infinity. However, for downward, it happens between 0 and 5. Okay. So for this example, find the first and second derivative of the function. So this is more of the practice on what we did. So just go ahead and try it. This is what you tested on, and see, of course, now as a practice to get this for a first derivative, and get this for a second derivative. Second one, and check them. So now similar, we want this, the question is concave up and down. Where does it happen and what intervals? So let's take the second derivative and discuss it. If you look at this part here, the denominator, you're going to see that x squared plus 2 is always positive. So really it's gonna matter whether the numerator is positive or negative to affect it. So let's find the critical value by setting these to 0. And don't forget this part again, it's always x can be 0 and 6 minus x squared can be 0. And when you solve this, of course, you find two values. So here we have three critical values. We have negative square root of 6, we have 0, we have square root of 6, and we need to test each part for f double prime. So you will, negative square root of 6 is about negative 2.5, right? About that, so here about 2.5. So you can take some numbers like a 4 to try there, and maybe a 1 to try there, and maybe -1 to try here, and let's say -4 to try here, right? So I'll show one, and you can do the others and test each one of them. So for example, I want test -4 means you're going to substitute in the second derivative, which is -4 times -2 times -4, 6 minus -4 squared all over -4 squared plus 2 cubed. So -2 times -4. So remember, this is where we substitute. -4 times -2 is 8. 6 minus 16 over 16 plus 2 cubed. So you see the bottom is not, you don't have to worry about it because it's always positive. 8 is positive times 6 minus 16 is negative 10, it's negative. So what happens is you have a positive times negative is a negative, right? Over a positive, which means negative. So in this place here, it's negative. And you can do the same thing. So do same check for -1, 1, these points that we picked, and see if you get these here. So it's important to test these and to know. So you should get a positive there, you should get a negative there, and you should get a positive there. And when this happens, that's it. Once you get these results, now you know where it concave up. It's between this square root 6 and 0, and square root of 6 and infinity. That's for concave up. And where down is negative infinity to negative square root of 6 and 0 square root of 6, right? So remember the same test. You take the derivative, so you use the quotient rule that we did. Once you have that quotient, you take a second derivative of it. And and sometimes this second derivative test is hectic because going into second derivative things sometimes may get simple and may get a little bit challenging. Like in this case, it gets bigger. And if it gets bigger, then we have to find the simplified form like this one. Then set it to 0, which means the numerator is 0, the denominator cannot be 0. And when you set the numerator to the 0, you get the critical values. And once you get the critical values, you test left and right of each one. And when you test left and right of each one, you find the signs there, whether the second derivative is negative or positive. And that will answer the concavity for this. And we'll finish this one and do some more examples in class. Thank you.